clear of voice traffic. Right, so a lot of places sell these little walkie-talkies where you can just punch in and listen. And if there's nobody on your frequency, that's probably a safe one to use. Follow the manufacturer's guidelines and workflows. One thing the GPS or GNSS surveying industry does well is every manufacturer puts out these highly detailed workflows on basically step-by-step, screen-by-screen, how to configure all your equipment. Follow those, extremely closely. Don't deviate from them under any circumstances because they have done this over time and they know what works and what doesn't. Always, always, always confirm the projection in units you're going to be recording data in. Okay, so this is highly important if you want to use your data when you're done, right, which is almost always the case. And lastly, the moment you get to the site, get your batteries in and get your GPSs on. Like I said, it takes time to acquire satellites, to lock, and to resolve that integer ambiguity. The sooner you get your GPSs on, the faster that's going to happen. Okay, now, we're getting very, very fast lock times now as the technology has progressed, but this is still a good practice, right? I take them right out of the case, batteries, turn them on, and then I just keep them in a safe location until I'm ready to mount them on the equipment and configure them. If you're on the network, some of this stuff still applies. First of all, accurate antenna height. So both the base station and your rover need to have accurate antenna heights. When you configure, the general direction is to use the data collector Wi-Fi now rather than a SIM card in the data collector. So most people are carrying Wi-Fi hotspots and using the data collector Wi-Fi to get corrections, to access the internet to get their corrections. So make sure you have a solid signal for that. Make sure your connection to the network is steady. So that's both the connection to the cellular network and the connection to the reference network. So make sure that whole pipeline is solid. Again, follow the manufacturer's guidelines and workflows. They'll probably have a completely separate manual for using a network or using a base station. Again, confirm your projection in units and turn your GPSs on as soon as you can. So when you're actually doing the survey, now everything's configured and you're out there, you're collecting points. Keep an eye on the diagnostics that you're getting on your data collector. So your DOP values, or dilution of precision. So these are values that are basically environmental factors that can reduce the precision of your measurements. So there are accepted values for DOPs, and there's a horizontal DOP, a vertical DOP, a positional PDOP, and there are a couple other ones. Also, your standard deviations. So you'll notice that your position, like I said when I showed you that little point cloud, right, you're getting multiple positions, so you can actually compute a running standard deviation. So you want that standard deviation to be as small as possible, right, which means you're as precise as possible, right? Your distribution of possible locations is very tight. So you want to monitor that and make sure you're within the tolerances that you have set. Now, when you're actually doing RTK surveying, your data collector will show you that you are in one of three modes. The first mode is autonomous, right? All this is saying is that you are a standalone GPS. You're just a person with a GPS. You're not receiving any corrections, or there's no communication with the network or the base. So you're getting standalone GPS accuracy, and that can vary, but usually the 3 to 5 meter rule of thumb is what you have for autonomous positioning, right? So autonomous means you're on your own. Float is the second mode, right? So you'll go from autonomous, and then you'll see it shift, and it'll actually say float. So float means that you are talking with the base, but you may not have enough satellites in common yet such that the integer ambiguity is not completely resolved. So it's still trying to figure out how many full wavelengths to add to that fractional phase difference at the end. So a lot of times it's called float because you might have like 6,372.812. So you have that floating point number. It hasn't yet decided which integer to use yet. So float accuracies can generally be sub-meter, but again, you only want to start surveying when you are under fixed mode. And normally all the software has a very, very pleasant ding sound when you switch into fixed. So you'll be in float, and then you'll hear that very happy like ding, and that means you are now fixed. So you have the integer ambiguity is resolved, you have good communication with the base, and you'll notice that your standard deviation will drop, and then here it'll drop to, if you're surveying in meters, it'll be 0.011 or something to that effect. And then general heuristic or rule of thumb is your vertical will always be half as accurate or half as precise as your horizontal, just because we can't have a GPS satellite on the other side of Earth to help us resolve the vertical position. So that's why it's generally about half as precise. So fixed is good. Everything's locked in and you are ready to get points. Most data collectors are set by default to only store fixed points. So it'll refuse to let you, it'll say your standard deviations are too high, and it'll say did not store the point. So when you I'll actually just bring this over. So when we get out there, you'll see that there is a bullseye level on the rod. So for that, we want to hold the survey rod, right, which is going to have a big antenna on the top of it, such that that bubble remains in the center of the bullseye. Now, if you're moving quickly, you might not have this bipod set up, so you'll just be holding it steady. Now, if you're not holding it steady, what are you doing to those standard deviations? Right, you're actually increasing them, right, because when you move over here, you get a position, and you move over here, you get a position, and here, and here. So you're actually artificially increasing those standard deviations. So that might cause some points to be rejected. So you the more you do it, you get better at holding it as still as possible right there. If you somehow can't do that, then you can actually stabilize it with the bipod, such that the bubble's in the middle, and then you store your point when it's absolutely still. Typically, we store 6 to 10 points per location. So I'll go here and I'll press survey, and the software will collect 1 point a second, and then it'll show me point stored, and then I can move on. I generally don't use a bipod if I'm going to be either moving quickly, or a lot of the work I do is in coastal salt marshes, so very, very dense grass, and the bipod would never be able to find a spot to hit. And if it did, it would be really soft. So, bipod is optional, but highly recommended if you need it steady. Also, the bottom of the rod. If you're surveying hard surfaces, right, you see how that's a point? That is ideal for hard surfaces. However, for soft surfaces, you might actually penetrate the ground. So therefore, you're getting an elevation that's a little bit too low, right? In a coastal salt marsh where I do a lot of my work, you would be weightier than you would. Just the weight of the rod alone would sink that thing in a couple of inches. So you have a point. You also have a topo shoe, which is basically the same diameter as the rod, but just has a flat bottom on it. And then you have an extra wide topo shoe, which is the same diameter, but it has a plate on the bottom of it that's a couple of 2 or 3 inches in diameter, and that's for really soft surfaces. Right, so consider that, and if you, for example, have to use a point on the ground, just be conscious of the fact that you don't want to shove that point all the way in, right? Keep it slightly above, or don't let it penetrate. So here are some final tips as to what you should do. First of all, I cannot recommend this enough. Make checklists, right? Have a checklist for office prep, have a checklist for when you get to the site, have a checklist for when you leave the site, and have one for when you get back to the office and are post-processing your data, right? Leave some white space on your checklist so that you can learn from your mistakes, right? We should have done this. You write that in and then you update your checklist, okay? After, always debrief. Sometimes this is just a conversation on the way home, right, in the truck. Hey, that didn't work out, we got to change that. What do you think? Okay. Always talk about it, and then ask a lot of questions. I find that the surveying community in general is pretty cooperative. They're, as long as you're respectful, I've gotten great advice from internet forums, and especially from the manufacturers. So they are, there to help you, and absolutely you should use that as a resource. So that's it for the classroom portion of this. A lot of the material, including a lot of the images, I derived from this textbook. This is a textbook that I use in the Civil Engineering Measurements course. And here is NGS's website, ngs.noaa.gov. That one's pretty easy. And the Florida Permanent Reference Network is, again, at this website right here, FDOT's website. So are there any questions before we get our hands on the equipment? All right, so let's get the stuff up and running, and we'll go outside and we'll actually configure the base station, configure the rover, and take turns collecting some points. Thank you very much for the opportunity. Is you always want the clearest possible view of the sky. Right, so this actually is, I would consider, less than ideal spot for the base station, just because, you know, we got a building there, so that's taking out a big chunk of our horizon, and then, you know, these trees will be somewhat difficult too. Normally, what we do is we actually set the data collector so that we mask out usually between 10 and 15 degrees of the horizon, because the satellites that are in that zone have to pass through the most possible atmosphere to get to us, and atmosphere equals dilution of precision, generally. So we want to avoid that. So, Mr. Spearing, right there. So this is a 2-meter fixed height tripod. So meaning that from the top of the plate down to the spike is 2 meters. So 2 of these are operated with hand clamps, right? So I can't squeeze that in. Who wants to try leveling this thing? So when you set up a fixed height tripod, Ali, will you open up the GPS case? It has a bullseye level, just like the rover pole does, except this one obviously has 3 legs and that one only has 2. So when you set it up, one of these legs is held by a screw, the other 2 held by hand clamps. Always make sure this screw is loose, right, at first while we're leveling. Okay? Yeah, go ahead and... Nope. So this is the GPS receiver we're going to use as the base station. Right, so when we take this stuff down, you know, we can take a look at it. So I'm just going to attach this to the top. So it just screws on there with a standard survey thread. And this is just an antenna for the UHF broadcast of the corrections. And again, I'm just going to turn it on so that we start acquiring satellites right away. And Ali, you can turn the other one on. There's a power button on the front. Press and hold that. All right, so Shiblu now is going to set this up. So he's going to grab both of these, and see this grip right here? Yeah, you want to squeeze that hard, or somewhat hard, and then slide it around such that you, make sure you're always squeezing when you're moving. So squeeze as hard as you can, and then try to get that bubble into the center of it. Yeah, it's kind of like a game. It's pretty fun. And then when you're in there, you just let go. Almost. Yeah. Gently let go. I could not have done that any better myself. That was a really good job. Okay, so now the base station is plumb and level. So now we're going to set up the rover and then configure the base station. Go ahead and screw that onto the top. the standard survey thread is 5/8 diameter by 11 threads per inch. And that's pretty common amongst all survey equipment to allow interoperability. Yeah, so gone. All right, so I'm going to use my data collector here to configure both the base station and the rover. So if we don't see any wires here, how do you think this data collector is going to communicate with these two GPS receivers? Bluetooth, right? Wi-Fi, not a bad guess, right? But we're going to establish Bluetooth connections between these two. So I'm just powering on the data collector, and this is actually, most data collectors run Windows Mobile operating system. This is actually just a small, rugged tablet computer, so this one's actually running Windows 10. So it's a little bit more powerful, but data collectors often run their own. Or if it's a data collector made by a particular manufacturer, it'll run their own proprietary operating system that really only does this. So the software I'm using is called ServPC. It's basically it's a software by a company called Carlson. They make survey software and survey hardware. ServCE is one of the software packages that is generally used by all types of GPS receivers. Right? A lot of the other data collector software can only be used with that brand of GPS receiver. Right? So there are many, Trimble, Topcon, Sokia, Leica, they all make excellent equipment. So just make sure that your data collector is compatible with your receiver. ServCE is generally compatible with every receiver, which is why I chose it to teach with, because a lot of times we get donated equipment and I want to have the most flexible possible system to use. So most data collectors are just a touch screen or a combination of a touch screen and a numeric keypad. So the first thing we do is we create a surveying job. Right? And that's basically the master file that contains all of the observations and other information about which satellites we were connected to and all these other stuff. And typically that's a group of files, not just one file. So I set up my projection and the units I'm going to use. That's very important. Like, you must know that you collected your data in feet or meters, because then when you try to upload it to GIS or something, you want that to be consistent. So I'm going to establish a Bluetooth connection with the base. So on the base, on the GPS receiver, there's a series of diagnostic lights. So I just heard it beep, so there's definitely a blue light blinking on that, and that says that we have a solid GPS connection. So the first thing we do is we specify the manufacturer and the model of the GPS receiver, okay? Because the distance that we know for antenna height is from the point up to the bottom of this plate. The actual antenna is located inside this little dome at the top, right? Or, various antennae are set up different ways. So that antenna actually has a phase center, which is where the actual vertical measurement is taken. So the software, in order to be compatible, or in order to support this type of receiver, the manufacturer sends Carlson, its phase center information. So it knows that it's about, 80 or so millimeters from the base up to the phase center of the antenna. So it makes that adjustment inside the software. So the Bluetooth is connected. Now I'm setting the antenna height. It's 2 meters or 6.5617 feet. This is where you specify the elevation mask. So I want to discard every satellite within 10 degrees of horizontal, right? So I'm eliminating the satellites that are highly probable to have a lot of atmospheric interference. And then the key part of this is setting up the RTK connection. All right, so I'm setting up this base station to use UHF radio to broadcast to the rover. I'll leave. Can you grab me another antenna from the case? Yes. So I'm setting this up to broadcast via UHF. So these are Hemisphere S320 receivers. So these use a internal NL400 microHard UHF radio. So I also must specify the frequency, right? So I'm going to not take my own advice and not check this frequency for voice traffic, right? But I'm going to broadcast on 445.45 megahertz. Right, so that's the frequency I'm going to use for this. That one's generally open. And I can also set the power. The maximum power is 1 watt. Right? As you increase power, you actually need an FCC license, so a Federal Communications Commission license, to broadcast at that power on some of these frequencies. Since I don't, I must keep it as local as possible. So you always want to use the smallest amount of power that you need to do the broadcasting. That'll save battery and other stuff. There's also different types of messages that contain the information being sent from the base station. So these are just a variety of formats. One is called RTCM, one's called CMR, and there are a couple older ones that aren't used as much anymore. But RTCM version 2, RTCM version 3, and then CMR, and then there are a series of modified CMRs that are manufacturer specific. So you must make sure that your base and receiver are both operating on the same frequency with the same message type, right? So once that's configured, I'm going to add a whip antenna to the rover so it can hear the UHF signal sent by the base station. So now the software is asking me to tell it the position of the base station. Right? It wants to know where the base station is. So I have 3 options: read from GPS, enter the lat long, or enter the grid system coordinates. Right? So grid system would be a projection, not lat long. So since I just set this up for demonstration purposes, I'm going to read from GPS. It gives me the option to enter if I want to do it by number or by time. So I'm just going to take 10 readings just so we can keep things moving. But again, we want to do at least 15.